It's a great pleasure to welcome Nick Hawker from First Light Fusion. So Nick started his research in 2007 as part of his master's thesis whilst a student at Corpus Christi in Oxford. He then went on, again of course in Oxford to do PhD, finished in 2012. Before he finished, interestingly, he co-founded First Light Fusion in 2011, and then in 2012, once finishing the PhD, he became CEO and Chief Technical Officer. So with that, Nick, off you go.
Okay, thank you very much. Thank you for having me. So I'm going to try and talk about a bit of everything that First Light does, and hopefully that will fit in the allotted time, but I'll do my best. So I wanted to start off with just kind of a context slide, and this is actually one of the slides which I use in the pitch which I give to investors to kind of explain what's going on. So it's really simplified. There's two broad camps of fusion technology: magnetic fusion and inertial fusion. And you guys know all this stuff, but my analogy, which I use to kind of explain the difference with this, is magnetic fusion. You're trying to build a furnace, so it's something which is always hot, always on. It's a steady state device, or notionally, it's a steady state device. And you have to, put more wood on the fire, and you have to get rid of the ash. So you have to put more DT in somehow, and you have to get rid of the helium, which is the ash, and the whole thing keeps going. And then inertial fusion, which is, I find, conceptually much harder to explain to the layperson, for sure. Magnetic fusion, big magnetic bottle. That's kind of, people get that, I think. Inertial fusion, I like to say it's more like an internal combustion engine. You put in some fuel, you have a spark, which causes the fuel to burn, and then you have to get rid of the waste from that, left over from that process. And it's the energy per event times by the repetition rate, which is what actually gives you the power output, which is the thing you care about in a power plant. Now I said that this is simplified. So there's an in between, of course, which is magneto-inertial fusion or magnetized target fusion or whatever you want to call it. So the kind of three leading projects, I think, this is JET on the left-hand side. This is, I think that's actually a picture from Amiga on the right-hand side, but the National Ignition Facility. And then there's Z Machine at Sandia, which is doing the maglev concept, as well as a whole bunch of other startups working on various flavors of magneto-inertial fusion. So that has aspects of both. It has a strong magnetic field to, depending on the scheme, reduce the conduction loss or trap the charged particles, and there's an implosion. Actually, I think what actually makes more sense to me, kind of, not trying to talk to the layperson about it, but talking to scientists about it. What makes more sense to me is it makes more sense to talk about it being pulsed versus steady state. But then tokamaks are actually pulsed, of course. So actually, the most meaningful distinction for me is about how you get around the gain limit. So there is a gain limit, first off, and it isn't. You can find that in textbooks. So if you look at the energy required to heat a 1D and 1T ion to the required temperature, and you divide it by the fusion energy, you get a ratio of 680. Basically, that's not quite enough, really, to actually run a power plant. So you need a way of getting around the gain limit. And magnetic fusion and inertial fusion get around that gain limit in different ways. So with the tokamak, it's about adding more fuel to the fire, and you don't have to pay the energy cost to heat up the next DT pellet. The reaction itself heats up the next one, and you bootstrap, and you get around that gain limit. Whereas for inertial fusion, ignition and burn, this is why you have cold fuel. It's so that you put 1 unit of energy into the hotspot, it releases 10, and those 10 go into the cold fuel, and they release 1,000. Or those are made up numbers, but that I find to be a more meaningful distinction between technologies. Is how they're getting around the gain limit. Is it ignition and burn? So maglev is ignition and burn, and any pulsed process has to be ignition and burn, or it's by refueling. So what First Light does, that's not the computer I'm using. This is the computer I'm using. Very good. What we do at First Light, we have a new method for inertial fusion. I think it's important to put it that way because we're not saying we're making up new physics here. We're trying to create the same states of matter as any inertial fusion, but it's a new method for doing that. And this is the simple, stupid diagram to explain it. So we call it projectile fusion. In the literature, people talk about impact fusion, so it's kind of similar to that. So basically, we launch a high-velocity projectile, which then hits into our target, and that replaces the laser. And the reason we want to do that is because it can be much more energy efficient, and the machine required is much simpler than the large lasers required. So we want to electromagnetically launch the projectile, and I will show you a picture of our electromagnetic launcher later. For the projectile, the most important thing is velocity. Now, if we make comparison to the laser world, velocity is more like the power, whereas the kinetic energy is like the energy in the laser. For us right now, our goal is to get to demonstrating fusion from one of our targets for the first time. Right now, we have plenty of energy, but it doesn't get delivered fast enough. So for us right now, velocity is the most important thing. Ultimately, it's the kinetic energy as well. You need to have enough energy to get to gain. You need to have enough energy. And then the projectile hits into the target or the fuel pellet. And this is where our kind of clever secret sauce lives. So the target has to work effectively with that one-sided drive, that one-sided impact, which obviously is a big difference between both NIF and maglev. So NIF is a spherical implosion, maglev is a cylindrical implosion. We have really complicated implosions driven from one side that nevertheless can get to very high temperatures and densities. But unfortunately, we keep all of that as trade secrets. So whilst I'd really love to talk about it, I'm afraid I can't. So I'm going to be describing the science that we do that goes into understanding that system. Rather, I can't talk about the system itself. I will say one thing about what the targets do. One of the things they do is they multiply the velocity of the projectile. So if you hit at velocity 1, something somewhere in the target implodes at a higher velocity than that. And our experimentally demonstrated record velocity multiple is 10.2. And that's the big difference from the previous impact fusion work. They didn't have that multiple. Yeah, and before I move on from kind of introduction, I just wanted to show this. So this is our mission statement. Solve the problem of fusion power with the simplest machine possible. And I wanted to bring this up because I want to make it clear that our mission statement is not solve the problem of fusion power with projectile fusion. It's just that we think that is the simplest way possible at the moment. And there is a compromise there because the target physics is actually harder. But we think that the onward pathway to the reactor is easier. So on balance, this is the approach we're pursuing right now until we discover something simpler or we discover it's not going to work. And then we'll have to switch to something else. OK, so I'm going to talk through a few things. First, I'm going to start off with some economic stuff about where does fusion fit in the energy landscape. Then at first light, inside the technical team, we have three teams. So pulsed power, building the electromagnetic launcher, experimental physics, numerical physics. I'm going to talk about what they all do. And then I want to show some work that we've done on how this more complex implosions can scale to gain. We've not solved the question, but we've done some stuff which helps to start solving the question. And then at last, I'm going to talk about a bit about our design vision for the power plant. So yes, the world needs every energy technology it can get immediately. So I want to sort of substantiate what I mean by that statement. So I just want to introduce a term, though, to start, because just in case not everyone's familiar. So the way that energy generation technologies are compared is through a measure called levelized cost. So the levelized cost of energy. And the definition of the levelized cost is as I've written there. So basically you take the entire cost over the entire lifetime of the generating asset, whatever it is. So if it's a nuclear power plant, it's over 60 years, and it includes a gigantic amount of capital expenditure up front, and then very little running cost, and then a gigantic decommissioning cost at the end. But that's in 60 years' time, so it's heavily discounted. So it doesn't actually. So it ends up. That's how you end up with problems with decommissioning, I think. But if it's a solar panel, then the calculation might be much, much shorter. It depends on the lifetime. And then you divide that by the total amount of energy that is generated over the entire lifetime of that asset. And that basically gives you a means, a like-for-like means to compare different technologies. Solar and wind are already the cheapest sources of electricity, which I think is something that is getting more broadly known. It's been happening for a while. It's been happening extremely quickly. You can see the falls in price. And I put it that way because people often talk about how solar and wind will be the cheapest sources of electricity. In the UK, onshore wind is the cheapest source of electricity, full stop. Cheaper than gas, cheaper than coal, definitely cheaper than nuclear. Even offshore wind is already beating gas in the UK. So coming back to that statement I made at the start, we need every source of energy we can get immediately. It doesn't seem to fit with this picture. So it's kind of as instructive to ask what's not the problem as it is to ask what is the problem. There is a problem. The problem is not cost. It's not that energy generation technologies are expensive. The cost is lower than it has ever been to generate electricity. It's also not intermittency. And there are a lot of studies out there looking at getting to very high penetration of renewables and how you manage that grid with those intermittent sources. And the answers sort of range between, let's say, 60% penetration of renewables to 100% penetration. I kind of argue about that, but fundamentally, I think it is possible to manage that grid. And even more so, the cost of doing so is not prohibitive. So I've added onto the numbers from the previous slide, I've added on the cost, well, I say this was done by a consultancy called Systemic for us. They added on the cost of intermittency, basically paid for with lithium-ion batteries and gas peakers to deal with the hardest intermittency to deal with, which is not when the sun goes in front of a cloud, but it's when it's summer, winter, that difference. So this isn't a carbon neutral grid, it still has gas in it. But the total cost of intermittency adds about $15 per megawatt hour to the levelized cost. So you take solar, for example, from 35 to 50. Well, gas costs 80. So this doesn't change the picture. Solar and wind are still the cheapest sources of electricity. So the problem, and this is where fusion fits, and this is where any new energy technology fits, the problem is scale. So this is looking at the growth in deployment of solar and wind in a global sense. And what our analysis has done is, I'm going to use the stick. So this is based on current policies. So this is the total sum of wind and solar based on current policies. We wanted the most aggressive situation, the most aggressive scenario for deployment of solar and wind, because we wanted to know the answer to the question, do we actually need fusion? So we took these curves. This is continued exponential growth. We did this last year. Reality is already behind this model because last year, 2018, growth in renewables flatlined for the first time. We assumed continued exponential growth. You add all of that up and you compare it to the total demand for electricity. This stands for current policy scenario, and this is something called the shell sky scenario. So if you're interested in learning about predictions for the future of energy, the shell sky scenario is a good one to have a look at. Renewables can get us to half of the required electricity generation. So a lot of the stories you see in the news take that number and compare it to how much electricity we need now. But electric cars are coming, right? Electricity demand is going to increase. If we're going to get to net zero, whilst overall energy consumption might be falling, the demand for electricity is substantially rising because actually only about 20% of energy is electricity. So, the energy in my car, and I drove here this morning, was not electricity. So that is what creates this clean power gap. And this is why ultimately we need new technologies. We cannot get to the scale required to meet net zero by 2050 with the technologies that we currently have. So this is what sets the market for fusion. Without fusion, what's going to happen? Again, this is very much my opinion. In my view, it'll be filled with gas because we simply can't build nuclear power. The empirical evidence is they're just not happening, right? And we will miss our climate change targets. We won't solve climate change. And my mission with First Light is, because I'm not skeptical about climate change, but I am skeptical about the world's will to tackle climate change. My mission is to build a technology that can straight up compete with gas on price, because then I think the world will switch away from gas, but not if it costs anyone any money. But if in that world, the good news is because of this gap, fusion doesn't have to directly compete with solar and wind on cost. It has to compete with gas, and the price point is higher. That means we can afford solutions which we otherwise wouldn't be able to afford. So even if the price is as high as $75 per megawatt hour, there's still a substantial market for fusion. And the market opportunity is still hundreds of billions globally. This is gigawatts of installed capacity. And this is where you're genuinely competing with gas basically worldwide. So yes, that is the good news. We do need, well, good news for fusion is we do need it. The bad news for the world is we need to get on with it, I suppose. Okay, so on to pulse power. So we have recently, at the start of this year, commissioned what we imaginatively called Machine 3. So this is our electromagnetic launcher. It's the second highest current machine in the world. Now, this seems to be, in contrast with our mission statement, doesn't look like a very simple machine. It's physically large, but ultimately it is actually a pretty simple machine. So the blue boxes are the capacitors, and the capacitors all discharge in parallel through the transmission lines. These things here with the kind of blue sort of squid on top, that's feeding dry air to the switches, so those are the switches. And then this is what we call the transmission line, and that takes the current into the vacuum chamber, which is in the center. So it's a big machine, but if you draw the circuit diagram, it's dead simple, right? So, the Machine 3 uses the simplest trick you can have to boost the voltage, which is that it's plus minus charged. So the top half of the machine is positively charged, the bottom half is negatively charged. The switch is all closed together. It goes through a quad plate transmission line and into the load. So this is Machine 3 in numbers. So total capacitance. It is a very low inductance machine. On the previous picture, you saw lots of sheets of plastic poking out everywhere. So that's the insulation for the machine. The reason we use that insulation is you can bring all the conductors as close as possible, and you can minimize the inductance of the machine. So the current rise time, which is probably the most important piece of performance for a pulse power machine, depends on the voltage and depends on whatever the inductance. So you want to push up the voltage and you want to minimize the inductance. So this is real engineering optimization, this machine. This architecture has been done before in a machine called Shiva Star, which doesn't exist anymore. But that was plus minus, I think, 45 kV. So we've pushed this architecture up to plus minus 100. Although that's in principle. We have commissioned it to plus minus 70 thus far, because we don't want to take any more machine risk than necessary to get us to our result. What that does is it delivers into a short circuit, it delivers 14 megaamps in 2 microseconds, which is that makes it the second highest current machine in the world. But it's slower. So the Z machine is the top machine, is the highest current machine. That does 20 megaamps, but in 200 nanoseconds. The current into the load also depends quite a lot on the load inductance. Because the machine inductance is so low, if you've got 12 nanohenries, if you add on a 5 nanohenry load or a 10 nanohenry load, it makes a big difference to the overall inductance. So the performance is quite coupled in that sense. So using the machine, something that has to be understood is that coupling. In terms of machine diagnostics, we have a lot of things going on. So we have VDOT probes scattered throughout the system. So those are the red dots. It's basically a capacitor which measures dVdt, hence VDOT. You integrate the signal and you can get the voltage versus time. BDOT probes are also scattered throughout the machine everywhere. This is basically a small coil which is sensitive to dB dt, hence b dot. Integrate those, and you get the current profile. And then to give us our most reliable current measurement, we have some Faraday lines. So these are fiber optics which are looped around the important conductors. So we have one per module, and then we have a total current measurement with a special fiber which basically you put a polarized laser down this fiber, and then the fiber, when it's in a magnetic field, causes the polarization to rotate, and you measure the rotation of the polarization. It gives you a direct measurement of field, magnetic field, which then you can convert to current. This shows an example of what we get from that. So this is, we call this the M3 infographic. So we have all of those diagnostics automatically saved, and then we've written a processing script, quite a substantial processing script, which takes all of that and chucks it up on screen for people operating the machine to see in 30 seconds after the shot what happened and how the machine performed. So we get, this is the raw signal of the Faraday, which I will not try to explain, and then you get the total current, and then this shows all of the B dots, raw B dots for all the different modules, integrated B dots for all the modules, V dots, and so on. So we're trying to do really a good job in kind of understanding how the machine is performing. This is working pretty well at the moment, so we have actually been able to do preventative maintenance based on having this infographic information. So if we see a switch fires late 2 shots in a row, we go and take it apart and have a look at it. And normally it's had a mechanical jolt and it's on the tilt or something like that. This is really important for maintaining machine health to have this sort of information. And this is the basic configuration which we're doing with the machine. So this is something called a flier plate. Various people have done this before us, including Sandia on the Z machine. So this is our electromagnetic launcher. So it's kind of like a miniature railgun. This is just a schematic, obviously, but basically we focus all the current into a very short section, not very wide, and it creates huge current densities. Current comes in through the end and then back. That flowing current creates a magnetic field, and then the J cross B force launches the projectile upwards. And this is drawn as one continuous block because that's not far off from the truth. So there's no actual projectile which gets sort of loaded in. What happens is this thinned out section, typically aluminium, gets physically torn out from the assembly and launched upwards. So you're pushing shock waves into all of this material all around, but as the shock kind of bounces around in here, this gets accelerated to higher and higher velocity. The material completely fails in these positions, and you have this thing thrown upwards. So the whole assembly kind of explodes quite relatively gradually, but one piece comes out at 10 times the velocity of the rest, which I will show you some videos and simulations and stuff of. A typical size that we would do would be 10 millimeters long here, 10 millimeters wide into the page, 1 millimeter thick. And then this is rather overscale because this gap is normally about 1 millimeter as well. We normally make it in 2 parts, so the top being aluminium and the bottom being copper, because you want this to not move, so you use a high shock impedance material, basically something very dense, and that causes it to put more energy, proportionally more energy into the projectile. Okay. On to experimental physics. The experimental team has spent most of the last 18 months figuring out how to diagnose the flyer performance, but then obviously their role is also to diagnose the target performance. So this shows the kind of real in situ setup for the flyer plate experiments. So the machine has 6-fold symmetry, 6 modules, and so we come in and we have, if I come from the outside, we call these these bits of metal here the pizza slices. So there's 6 of those. They come into this piece of copper here. This is a mechanical fuse, so that the section in the middle gets destroyed during the shot, but this is designed to break, which means this then doesn't break. And then the actual load section in the middle is this hexagon in here. and then that takes the current round, and then underneath this black tube is where that flier plate system is located. The black tube is on there to screen out all the various other plasma that comes from this system. So I suppose this is something that we have learned about machine 3, basically because it's a high current machine and a longer pulse machine. There is, firstly, because it has so much energy, its raw capability to turn metal into vapor metal into plasma is extremely high. And then because the time is quite long, there is lots of time for that plasma to get to exactly where you don't want it to be, like between two conductors so that it shorts out, or in front of your diagnostics. So the plasma will expand out into the vacuum chamber at 50 kilometers per second and include everything. So what we do is, for the optical diagnostics, we have this 3D printed tube which comes in here that actually mates directly onto the top of the target. So our standard diagnostic setup is we have the flier plate. It launches a small distance, and then it hits into a block of PMMA or Perspex, which is transparent. So the visor line which comes in and down this tube goes straight through the block, reflects off the flier surface, and comes straight back out again without being disrupted. And then it allows us to measure the pressure on impact. So what we actually see in that block is the shock speed. You can convert shock speed to pressure. The shock speed depends on the velocity, which we have an independent measurement of, although not always up to the time of impact. So it depends on the projectile velocity, and also the projectile density, so we get a decent amount of information. The diagnostic tube literally touches and fits around the target, and it has two mirrors in the bottom there to allow the backlit imaging. So the shock basically blocks the beam. We call it shadography. I don't know if it's really shadography, but and then the other thing we have is a wide field of view camera, which is just kind of a what happened, where did it go wrong kind of diagnostic. So first, this is one of the videos we get from the wide field of view camera, which I include because it's cool. You don't really get much quantitative information from this, but you get a sense, an intuition for like what's actually happening. So this is one without the diagnostic tube on top, so we can see what's happening, and you can see what I mean about there's just plasma everywhere. I'll let it play again. So this is where the flier plate is. So you can see it kind of grows, and there's plasma, and then something punches out at much higher velocity. So that underneath that cloud, in that cloud, is where the actual projectile is. Yeah, then in terms of kind of quantitative information, this is an example of the sort of visor signal that we typically get. So this is a 10 by 10 by 1 aluminium flier plate, like I was saying. It's kind of a standard thing. So it shows some typical features. So, well, firstly, here are the fringes. And then you can see the projectile starts to move. The front surface starts to move at this time. You see the fringes shifting. And you count the fringe shifts and the velocity per fringe to give you the velocity. So this one got to about 4 kilometers per second. Before we lost signal. There's this period in here where we are not measuring the velocity, but before impact. And so we think, by comparing through the simulations and a few bits of experimental evidence, we think that is a reduction in reflectivity as the front surface of the projectile melts. So this projectile is actually in quite a complex state, which we try and understand if we're going to understand the performance of our targets. It also shows some other typical features. So we normally see loss of signal at the edges. We think because the projectile is distorting as it flies up. It does so at the edges first, and the beam is reflected out of the path of the collection optics. And we also see a bright flash, which is very tempting to think it's the projectile hitting into the target. Unfortunately, it's there when there's no target as well. So there's at least two mechanisms for the production of that bright flash. So basically, what we've seen is that, and what we see in the simulations is the projectile launches, and there's sidewalls on the projectile, and that helps stop the magnetic field from coming around the side until the projectile exits the chimney, we call it. At which point it can then pinch, as all high current things eventually do. So we think we've seen that in the imaging, and it looks like this flash is correlated with the pinching. and there's also a flash from impact. So it's hard to say what that is, but it's basically there in every shot we do. Okay, so that's the visor, and then this is an example of the streaked shadography that we use. So we use a high-speed imaging camera on the shadography line as just what's going on. And then we also use a streak camera because it gives us better temporal resolution to measure the velocities. So it's not super exciting. These are timing dots. This is the time of that bright flash from the previous image. This is the backlighter, which has an unfortunate speckle pattern. So the only laser we have at the minute that's bright enough is the one that's suitable for the visor. So we'd like to have a less coherent laser, so we get rid of that and get better shadography, but nothing else we have is bright enough. And then basically what you see is this straight line is the shock, occluding the backlighter. And this is what we hope to see, basically. So we want a straight line. That means we have a shock with a sustained pressure behind it. If it's kind of a blast wave type shock, what you see is this slowing down over time. What we need for our targets is a sustained pressure pulse. Our present launch performance numbers. We think we're getting velocities up to about 15 kilometers per second at impact. That's sustained impact pressures about 100 gigapascals, which is 1 megabar, I think. And we have got higher pressures than that, but they're with this blast wave profile. So we're trying to kind of understand the parameter space of this system to try and optimize. Just to give you an example, we made a change to the flier thickness. We went from 1 millimeter to 700 microns, so 30%-ish change. And one of the pressures that we measured was 3 times lower in that case. So it's quite a nonlinear system. So we have a power loss issue. So we have done a lot of work to rule out what it can be. But basically, if we compare simulations and we compare simple kind of ODE models to the measured system, we're getting about 50% more current than we expect. But the strange thing is that the velocity matches our predictions. So basically, we think we have a small parasitic, well, not small, a parasitic other path, which basically allows the machine to deliver more current, but actually the current in the flyer plate doesn't seem to be very much changed by that. So I don't know if anyone here knows anything about this sort of stuff. This is not unusual. Z machine has a power loss issue, which they've been trying to solve for a decade. So we have found the same thing. It's a very different system because it's not vacuum insulated in the load. It's insulated with plastic. So we're trying to understand what that is at the moment. Okay, moving on to looking at target performance. Machine 3 is the newer thing. Most of our target development, including that record velocity multiple of 10.2 that I mentioned, has actually been done on a much simpler machine, which is our 2-stage gas gun. So basically you have a powder charge which launches off at this end, which launches a projectile in this tube, which is filled with hydrogen. That slams into the central section, compresses and heats the hydrogen. You have a bursting disk which opens up. That launches a second projectile, which gets to much higher velocity. So we can get up to 7.5 kilometers per second. And if you're using dense materials, actually it can get to the same pressures as machine 3. So if you have copper hit copper, you get megabar pressures. This is an example of the sort of work which we spent quite a lot of time doing, maybe 2 or 3 years ago. So trying to verify some of the hydrodynamics which go into our targets. This is a simple example where we have a projectile hitting a piece of plastic, and in the back of the piece of plastic there's been a hemisphere machined into it. And that hemisphere, when the shock hits, involutes, turns into a jet, and the jet propagates out. And you can see the experimental image is underlaid under both, and the simulation image is overlaid on the top. And you see there's really good agreement between the two. This sort of shows a mechanism by which you can multiply the velocity, because that jet goes at about 1.5 times the projectile velocity. But obviously we've got more complicated things going on to get to 10 times. We've spent quite a while doing optical diagnostic work. And then something we added is an X-ray capability. So we have been using an X-pinch as a fast and bright X-ray source. And as far as we know, this is a novel combination to have a source like that and a gas gun together. Basically, in X-pinch, you have some number of wires. So you put the wires in, and then you twist the setup so that they form a cross. And what people say it does is it localizes a Z-pinch. So if you just have a whole wire and you put a load of current through it, it pinches. But you get various different hotspots forming along the length, because instabilities come in. It doesn't pinch uniformly. It turns into sausages. And it's not very useful for imaging because you can't tell where those spots are going to be beforehand. So with the X-pinch, you basically make a really tiny, tiny section in the crossing point, and all the current gets dumped there, and that itself Z-pinches, but it's so tiny that only one mode of the oscillation of the frequency can develop. So you know where the X-ray source is going to be produced. And then there's also a cool mechanism where, so this is from a paper, so this shows the pinch happening, and the pinch, the neck, breaks, and it turns into like a plasma diode, basically. So there's still a huge voltage dropped across that gap, and electrons get accelerated from one side and then slam into the other and produce non-thermal equilibrium hard X-ray source, which is also useful because some of the materials that we want to look through are quite dense. This is an example of the sort of work we've been able to do with that system. So it's just a pretty picture at the top, so just radiography. This is the open back cavity, but at late time, and you can see the projectile is inside and is deformed during that impact. And then we've also been able to make quantitative density measurements with this system. So this is the X-ray image, and this is the optical image of a test experiment which we did. So basically, we have the normal projectile. We have a small piece of copper, flat disc in the middle, which is only the projectile diameter is 12.7 millimeters, and we have something like a 2 or 3 millimeter piece of copper in the middle. What that does, we hit that into a like 1 mil thick sheet of aluminium, and it basically, where the copper hits, it drives a much stronger pressure, and it kind of punches out a little center section of the aluminium. So what happens is you create a shock, the shock goes through the aluminium, and then it reflects from the rear surface. We're interested in what's happening on that reflection, because that's what happens basically anywhere in an ICF target somewhere. A shock has to break out from something dense into gaseous DT. And the reason we've done the experiment in this configuration is because we can then invert this to get back the density profile. So then this is a map of density. I'm going to come back to this and show a comparison to the simulation, and you'll see why we're kind of doing this. Okay, and then this is just something for future. So this is an example of the spectrum that we get from our X-pinch when we're using tungsten wires. I said our X-pinch. It's really Simon Bland's at Imperial, so I should say that. He's very kindly lent it to us. So basically, looking at this line in particular, we're quite interested in whether this could be used as a scattering measurement in some way. Don't ask me hard questions about that because I'm not going to be able to answer them. So, but that's what the experimental team are kind of thinking about for the next steps with this. Okay, last thing then, final experimental thing. Obviously, we're a fusion company, and our current milestone is to demonstrate fusion in the real world from one of our targets. So we need some neutron detection capability. There are positives and negatives for all the different techniques you can use. Basically, we've chosen PMTs with a scintillating plastic. The reason we've done that is the sensitivity is highest. It also offers the possibility to do more fancy stuff, so time resolve stuff, time of flight measurements, all that sort of thing. The big issue with them is you get false positives. So if you have X-rays hit your scintillator, it can scintillate. If you have charged particles hit them, they can scintillate as well. So basically, what we kind of commit to in doing this is doing a good job with the null shots. So we put hydrogen in, and we verify the signal goes away. We do deuterium, but we put lead in front of the detector. The signal should still be there. We do deuterium, we put plastic in front of the detector. Signal should disappear. And we do So we kind of have to do all this due diligence to make sure what we're seeing is really neutrons. Okay, very good. Moving on to numerical physics. It's kind of a statement of the impossible, but attempting to build predictive capability, but that is the goal, regardless of how hard it might be. We have two main code bases. Something called HyTrack, which is a 2D hydro code, which uses something called front tracking to represent interfaces between different materials. The interface dynamics are really critical to most of our targets. And it actually has an AMR grid, so adaptive mesh refinement. It puts the resolution where it needs it to be. This is a comparison so instead of the open-backed cavity, we have a target now with a full spherical cavity inside. And you can see there's light emission coming from that. So this is when the jet is crossing and there's a shock in front of it. We see that. The green, is the simulation overlaid on top of the experiment again. The jet hits the far wall, and then you get this torus of plasma in the simulations. It's there in the experiment, and you can see it fading away. So it's kind of cool. And then we also have something called Code B. Again, we're really imaginative when it comes to naming things. So this is a 3D code. Takes a very different philosophy to the kind of numerical physics. So this is very straightforward methods, and it's a uniform grid and all that sort of stuff. And it's our MHD code, resistive MHD. So this is an example of a simulation of the flyer plate. This is then that flyer plate section which we're shown in the schematic. And if we wait for it to go back to the start, then you see the current flowing on the inner surface of the flyer plate here, return path underneath. The current is penetrating through as it heats the material, the resistivity increases and the current penetrates further into the material. And the projectile, the flyer plate, is being launched upwards. Further physics, radiation. So at the minute we model it simply as loss. It's with a local escape probability method. So you take Bremsstrahlung loss, but then you look at the cell you're in and you figure out what the optical depth is just in that cell. So you can tend away from, when you are optically thick, you're not just losing Bremsstrahlung loss, which is unphysical. We find a very small sensitivity in our current target designs to the radiation. So basically, we run with radiation on and off, and it makes very little difference. So we haven't pushed into doing this in more detail. For a gain experiment, it definitely makes a lot of difference. So we will be adding multi-group diffusion approximation in due course, but it's not a big deal for now. Something that does matter more is conduction physics and two-temperature physics. Conduction is easy from a numerical point of view, much easier than the hydro. But if you use simple methods, so if you just use first order explicit Euler in time, second order central difference in space, you have a stability requirement which goes with the grid size squared. So as you want to get to higher and higher resolution, it disproportionately kind of kills your performance. The hydro modeling goes with the grid size to the power 1, so just with the grid size. So conduction always ends up dominating. So we use, some people use implicit methods, where basically you have to invert a matrix every time step to do that, which can be unconditionally stable. So you can take bigger time steps. We use something called super time stepping, which is still an explicit scheme, but allows you to take much bigger time steps. It's just magic. I don't know how it works. I'm not sure anyone really knows how it works, but it does. In terms of two-temperature physics, basically you can think of the fluid as a two-component system. So the last point here, so if you look at energy exchange from electrons to other electrons, that happens extremely rapidly. So the electrons themselves reach a Maxwellian distribution very quickly. And then if you look at ion collisions, again, the ion distribution reaches Maxwellian extremely quickly. But basically because of the mass difference, the collisions between the two sets of species transfer energy much less effectively. So the timescale for those two to take a common Maxwellian distribution can actually be long in comparison to the total problem. So the way this is captured is by modeling it as a two-component system, our model assumes that basically the electrons are an unshockable gas, unshockable fluid within this system. So like a fluid with an infinite speed of sound, basically. So they're just isentropically compressed and decompressed as they're kind of evected around with the whole system. In terms of conduction, you can work out the conduction from the basically mobility of the electrons down temperature gradients, and then you can work it out for the ions in similar, and you find out that basically again because of the mass difference, the electrons are much more mobile. So most of the heat flux which is carried around by conduction is carried by the electrons in these systems. So then that's where it starts to matter. If you don't get the electron temperature right, you're not going to get the electron conductivity right, which is why you need to model it as a 2T system as well as other things. Our system's quite different to a laser. So lasers couple into the electrons, whereas these kind of hydrodynamic shocks that we're working with couple into the ions. So the ions get preferentially heated. So I've got this sketch to kind of show you what that means in a bit more hopefully physically intuitive way. So this is actually a test case for the code. It's something called the Shafranov case. So what you have here is a shock. And if you weren't worrying about all this 2T physics and so on, it would just be a density jump and a temperature jump, just one temperature. But what actually happens is the shock couples more into the ions than into the electrons. And the way I sort of think about that is that most of the kinetic energy is in the ions, and the ions which ahead don't know this shock's coming on, and the ions behind are rushing forwards in that direction. They slam into the other ions more effectively than they slam into anything else, so they put their energy into the ions. But then the conductivity acts on this whole system as well, and that changes how the dynamics work. So you have a jump in ion temperature, and that leads to conduction, which can take energy actually from behind the shock front to ahead of the shock front. So you have this little foot in the ion temperature from the ion thermal flux. And then because the electrons have a much higher conductivity, you have exactly the same effect, but even to an even greater extent. So in front of the shock, the electrons are hotter than the ions. And actually, the electron conductivity is so effective that you don't really get a jump in the electron temperature at all. It just kind of this smooth transition, because any jump that you would get here gets immediately washed out by the fact that the conductivity of the electrons is really high. I put at the start that I had 2 physics challenges to mention. This is the first one. We get really 2T states we've been learning, and I think in a different way to other systems. So we get 2T states with the temperature of the ions 10 times higher than the temperature of the electrons, and we're not really sure about what that means in like a kinetics kind of sense. I don't really know any literature about that. So that's the first physics challenge to kind of check out there. The equation of state is really important. I'm short on time, so I'm just going to skip through this. The equation of state describes something called the saturation region. So this is where you have both liquid and vapor states together. And this is a really difficult region to model, because you can get things like metastable states, which is what's happening with the water bottle. So it's water that's been cooled to less than 0, and it needs an activation energy to trigger solidification, and it freezes really quickly, which is cool. We've discovered this happens in our targets. So this is the second physics challenge to check out there. And we've discovered a really sharp threshold in behavior. So if we hit a piece of aluminium at 7 kilometers per second, it shocks to a liquid state and it releases to a liquid state. If we do it at 8, it shocks to a liquid state and releases to a mixed liquid vapor, I don't really know what, state. But we've made a tiny difference to the velocity, and you've got a 3 order of magnitude difference in the release density. And it's really sensitive to gas pressure. And that's why we did that X-pinch shot. And this is the comparison of the density line out from the X-pinch shot with the blue, which is our predicted density. So we're very pleased with that result. This is aluminium, so solid density for aluminium is up here. So this is an underdense state. And the interesting thing about this is this continues to happen all the way up to maybe 100 kilometers per second before you unambiguously shock to a liquid and release to something which is definitely a vapor. If you're in the saturation region, you don't have any clue what's happening really, and it's not really captured by the equations of state. I am very short on time, or I've got 2 more sections which I can perfectly happy to skip over, or we can do one of them, or I can do both. I don't mind. What do you guys want to do? So there's the talking about gain, and there's talking about the power plant.
Do you want to hear about the power plant?
Yeah? Okay, cool. Let's skip through this stuff then. Okay, so how does this actually look like in a power plant? The most similar concept in the literature is something called Highlife. So if you want to look up something in the literature, look at Highlife. This again is a slide from the investor pitch, right? So this is extremely simplified, but there is some truth in it, because each of these things are indeed very big challenges, known to be big challenges from basically tokamaks, tokamak engineering. So preventing neutron damage, producing enough tritium, so you need to be self-sufficient in tritium, and then managing the extreme heat flux in the device. So we think we have a design, very similar to the Highlife design, which avoids these 3 challenges. And this is the basic concept. So this is the reaction vessel here. And this is similar to an existing technology from nuclear power, which is the fast breeder reactors. So some fast breeder reactors are pool-type liquid metal systems. They're cooled with liquid sodium. There's a big pool of liquid sodium. Below the surface of the pool is the nuclear core, and the sodium is circulated round to take the energy away. So it's the primary coolant. So our idea and the Highlife idea is very similar to that. So it's a pool of liquid lithium, though. The lithium is required to make the tritium. And obviously we can't have this whole projectile hitting the target thing happening in a load of liquid metal. So the idea is there's a vacuum pulled above that pool, and basically we drop the target in from the top of the device, and we fire the projectile down after it through the same aperture. So the target's falling, and the projectile comes in on top and hits it, and it's timed so that it hits just above the surface of the pool. And then the key thing is you pump out some of that liquid metal, you bring it up to the top of the reactor, and you let it fall under gravity as falling liquid metal curtains or waterfalls. And this is what provides shielding for the near structure. So the neutrons, when they come out, they hit, if you put a solid material in the way, they hit into the solid material, and they cause generate knock-on ions. So they punch an ion out from its hole in the crystal lattice, and it's quite an energetic ion. So that then goes on a big cascade process, which knocks a load more ions all out of their position. And as that all resolves, some of them end up not in the right place, and so you end up with dislocations forming, and ultimately, on a macroscopic level, you end up with a material which is much more brittle than it was before. This is one of the problems we're trying to avoid. So by having all this liquid metal around, the neutrons, when they come out, they hit into the liquid metal, and you can't destroy the crystal structure of the liquid, right, because it's a liquid. And then most of the neutrons are absorbed inside the liquid metal curtain. Some come back out, but basically the first calculations we've done of this show that the lifetime of this vessel can be increased to be greater than the lifetime of the power plant. So in a tokamak, the first wall has to be replaced every, I don't know what it would be, 2, 3, 4 years, depends on your design point. That's a big challenge. It's a big remote handling challenge to do that. And ultimately for a power plant, it's a big availability challenge. So availability is the percentage of time that you're on and generating power. And that is one of the biggest factors in the economic model, is your availability. So if you can avoid that replacement, you're doing well. Now we still do have one component which has to be replaced. So this is what we call the reactor head. So basically we've put every penetration required into this volume into one component on the top, which would probably be about 2 or 3 meters in diameter. So it's still large, it's still going to be activated, it's still going to be damaged, but hopefully it's much easier to replace simply by being physically smaller, and secondly by being on the top. You don't have to disassemble all of this in order to get at that. So that's the concept in a nutshell. We had a project actually with UKAA funded by BAYES to do some calculations on this. So that's how I know that the neutron damage problem can in fact be avoided. And we also know that it is possible to get to tritium self-sufficiency with this system actually relatively easily. Basically, you have a very large solid angle available for making tritium, because there's just lithium everywhere. the main goal actually of that work we did, that project we did, was to pick the coolant out of the different candidates. So we looked at pure lithium, we looked at lead lithium, and we looked at FLiBe. Both lead lithium and FLiBe offer a way to multiply the number of neutrons and a way to up your tritium production. Basically, we found we didn't need it. And in fact, we didn't need to enrich the lithium either, which is a big deal, because then if you're using natural lithium, that's the existing supply chain for batteries, whereas there's not a supply chain for enriched lithium, so this does make a big difference. And this sets the thickness of the curtain, so it needs to be about 1 meter to work. Actually, the cost of the plant isn't very sensitive to that thickness, which sounds weird, but basically this is quite a small part of the whole compared to everything else. Okay, so yeah, we think our reactor concept does avoid these 3 challenges, but obviously with something very new, there's opportunity, but there's also risk. So have we added something which is just completely unsolvable? We don't think we have, but we have got a list of the uncertainties which worry us most. And the top one is meeting the frequency requirement. So firstly, we've mitigated the challenge by setting our frequency that we would like in the first of a kind to 0.2 hertz, which is 10 times slower than other designs for ICF. So that does mitigate the problem. The challenge is not really in meeting the frequency requirement with the pulse power. That can be done. The thing I'm most worried about is all the replaceable parts, basically. So the target is a replaceable part, and the projectile assembly, that hexagonal piece which I showed you, that has to be replaced every shot. And it's that one that I'm most worried about because it's bigger, simply. The reason that's not just a straightforward problem, it's got to go from outside vacuum to inside vacuum. It's got to go from outside the hot cell to inside the hot cell. It's got to go outside the tritium boundary to inside the tritium boundary. So these are difficult requirements. I think it can be done, but I think this is the biggest challenge in the design. We do have different options, alternative designs. So I have actually done quite a lot of work on what we call a linear launcher. So basically like a really long coil gun type thing. If we do that, then we can't drop it in from the top, it has to come in from the side, so that's a difference. It does make things more complicated. But there's no projectile assembly, there's just the projectile itself and no extra material. So that does make the rep rate requirement easier. And we're also interested in a laser driver. This is completely consistent with a laser driver, this power plant vision. It still has to be driving a one-sided shock, because the thing which I think is making the power plant much easier is the fact that there's only one penetration into that hot cell. If you imagine NIF and it's 192 lasers, it's 192 penetrations into that central system. That's really, really challenging. Reducing it to 1 lessens the challenge. But the only way a laser is going to be viable is by being dramatically cheaper. So it needs to be, in my view, at least 100 times cheaper than the NIF laser to be economically viable. Even with our system, which actually per joule of energy is 1,000 times cheaper, even with our system, the driver is one of the biggest costs in the reactor. The second thing, this is the final thing, lumps together a whole number of uncertainties, and it's all to do with managing that lithium system. So there are some big components to the lithium system, like the heat exchanger, but we think that that's close enough to the technology for fast breeder reactors that it could port across without huge amount of risk. But there are a number of specific subsystems which are bespoke to fusion and bespoke to lithium. So tritium extraction is one of them. Controlling the impurities in the lithium, so the spent target and the spent projectile, all of that material will end up in the lithium, and it will build up, and it could be 10% of the total mass over the course of a year, so it does need to be dealt with. There are ways to do that, but basically this sort of ancillary technology is kind of between TRL 3 and 5. So what we would like to do at the next stage is try and get this all to TRL 6, which is to test at a subsystem test at full reactor scale. So we want to build a lithium test loop, and this is a picture of the world's biggest lithium test loop, which I found out the cost for, and we think we will be able to afford to build a actually larger system at the next stage. So let me go on to conclusions. Yes, I hope you see, hopefully, what we're doing and what I mean by this by this statement. Whilst the whole liquid metal waterfall curtain thing sounds pretty mad on first thought, by the time you dig a bit, it does actually lessen a lot of the most difficult challenges in fusion engineering. And we think we have a credible plan for developing that. And in terms of where we are on our stage, we've got this milestone to hit very soon, which is to show fusion. and we're confident we're going to do that. Then we're going to be raising more money, growing again, so we're going to be hiring. And it'll be a 5-year plan to build and execute a GAIN experiment. And if we knew it was going to work, we wouldn't have to do the experiment. But I'm very confident we're going to build the experiment, and I'm very confident we're going to do it inside 5 years as well, if we get the money. And if we get fusion, then I think we're going to get the money. So, and then we also want to try and get to a completed conceptual design for the power plant with all components at TRL 6. I think that's enough to then immediately start the first of a kind plant. And so yeah, I wanted to finish with a point about timeliness, right? So if fusion is going to contribute to solving climate change, if we're going to contribute to getting to net zero by 2050, we need 10 plants on the grid in the 2040s, because 1 gigawatt isn't going to help. To do that, we need the first of a kind in the 2030s. And for me, to do that, we need to solve the physics problem in the 2020s. And actually, ITER's on track to do that. So if it gets built by 2025, then the device will be there and ready. Waiting to 2035 to do the full DT shots, though, in my view, is too late. So the program is going to have to take more machine risk than perhaps they're comfortable with right now. There's a whole bunch of other programs out there which can meet this timescale, but that's in my view what we need to do as a community. It's challenging to see how to meet that timescale with a tokamak. It doesn't mean it can't be done. So looking at all the MSc students here, it could be your idea, which takes a decade off the timeline, right? If you can figure out some new configuration where the plasma physics still works, but one of those engineering challenges is just knocked out by some change to the system that you make. That's the goal, is to find those kind of inventions. All right. Thank you.
So those who need to go, please do feel free. Right, so we've got time for questions. So any questions? Go ahead.
So your repetition rate, the frequency at which your machine is working, is lower than that of kind of conventional ICF plant. Does that imply that you expect to have higher energy yield per shot?
Yes, it does. Yeah, and the total, quite a big unknown in any kind of ICF plant design is what's the biggest amount of energy you think your plant can handle. The bigger it is, the easier the physics, and the closer you get to physics, which is definitely proven. But as you get bigger, your driver cost increases, and your plant cost increases. So what we've done in selecting that design point is, and we've kind of picked a design point, and we're kind of going into it knowing that we might find out that it's complete nonsense. We have to pick a different design point. But we've picked that one on the basis of, well, our driver should be a lot cheaper, so let's try and make the physics easier by having 10 megajoules in the projectile, not 2 megajoules in the projectile. And it's all trying to like circle around that concept and see if that can work. Yeah.
So in conventional ICF is quite sensitive to instabilities. Like you've got to have a very nicely shaped target, and the driver has to come in just right, or if there's some slight asymmetry, it all goes wrong. Right? Presumably the same is true to some extent with your, although it's a one-sided design, it has to kind of hit straight on at the right angle and stuff, or it'll go bad. So how feasible do you think it is to do that with the target and the projectile flying through the air at the same time, and for it to all hit in the right place at the right time at the right angle?
Yeah. Yeah. That's one of the challenges. Yeah. And to me, that one boils down again to the projectile assembly replacement. So I'm confident you could drop the target accurately because it's quite a gentle process. You just have to precisely let go of the thing and understand that it's center of mass and manufacture it precisely enough so it falls precisely. And it's in vacuum, right? So there's no like aerodynamic forces to cause it to start to tumble or anything. If you let it go right, it'll fall right. But then the projectile launch in our current concept, the linear launch is different, but in our current concept, it's quite a violent process. It gets to the required velocity in like 10 millimeters. So we do understand something about the things like tilt and the variation in direction and so on from the simulations. And you're going to need to load in that projectile assembly with a certain precision, which we don't really know at the moment. What I can say is that you can compensate, but by basically accepting a performance penalty. So if you oversize your projectile by 1 millimeter, you can cope with 1 millimeter of positional, offset. But you have to invest more energy because you've got a bigger projectile, so it comes at a performance cost. If your projectile has tumble, the front face is not hitting true. If you make it slightly convex, then you can compensate for that to a degree. But your energy coupling will be less good, and you're making a projectile assembly more complicated and more expensive, and so there are things that you can do, but that is one of the challenges. Yeah. On the instabilities point, which is right, so that's the answer from the power plant point of view. The answer from like the fundamental physics point of view. There are things which are unstable, which are common in both cases. If you have a shock breaking out into gas, that's Riemann-Merschkow unstable, and it always will be. But the problem with NIF is actually instabilities even earlier in the system. The laser ablation process, which causes the acceleration and the start of the implosion, that's unstable. That's Rayleigh-Taylor unstable. And Rayleigh-Taylor grows exponentially, whereas Riemann-Merschkow grows linearly. So we don't have an equivalent of that earlier time Rayleigh-Taylor instability. So our system has instabilities, but they're different. I think this is one of the reasons why the fusion result, even though the number of neutrons we're going to get is going to be very low, but it's why it's such an important kind of proof point, because we'll have made the target in a normal workshop. It'll cost £100. It won't cost $1 million like the NIF target. If that works and that matches our simulations, I think that we can sort of assert that we have a much more robust design, because it has all those imperfections in there. If it still works, we'll find out if that's true. It might not be true, but we'll find out.
Following on the similar kind of thought process, what's the repeatability of the projectile lines? The way you described it was the aluminium ripping itself from aluminium grounded. How repeatable is it to have the front go in the same direction on the same tilt?
We don't really know right now. Basically, we haven't had time to set up the set of 10 shots and look at the repeatability. We're kind of always changing the system to try and optimize. As much as you can tell when you're not just doing a dedicated repeatability study, it seems to be okay in terms of repeatability. But yeah, we don't really know. We haven't got time to do those shots right now. We'll do them after the result.
That was exactly my question.
Okay.
I have another one about liquid lithium. How do you think it's be manageable? Because presumably you have taken account of what happens when it leaks and comes in contact with air.
Yeah, sure. We've thought a lot about that. We're going to be starting a proper safety case analysis quite soon, hopefully. So yeah, those hazards need to be managed inside the plant, right? So for meeting that timescale, which I said, if fusion is going to contribute to net zero by 2050, the regulations is one of the critical things on that path. And it's important that we, the fusion community, recognize that the plant will need regulations, but that the government also realizes that it's not the same set of regulations as fission. There is radiological risk, right? If the lithium leaks, then there's a risk of tritium leakage. And that's a radiological risk which needs to be managed. There are things you can do. So you can have an argon blanket. So you put the reactor vessel in a double-walled thing with argon in between. That actually is done already for the fast breeder reactors. They use argon cover gas. They use double-walled pipes, that sort of thing. It all adds cost, But so I'm not sure. Yeah, basically, lithium fire in the primary circuit is probably the biggest radiological risk in the power plant.
Let's thank Nick. So thank you very much for a wonderful talk.
Thank you.